Hey everybody! I thought we would talk about the Bartlett test, which of course I put on there and didn't explain in class. So what we're going to do is take a look at some of the stuff on it so you can answer question 4. So I'm going to do 2 examples and I think it should clear up a lot of the questions for you. So we're going to have a test for one-way ANOVA that's similar to the VAR.test for the 2-sample test. So we use what's called the Bartlett test for one-way ANOVA. You'll see later that there's another one that we use for randomized block design. So we use this on the AOV, or excuse me, right before we run our AOV process. And we're going to use the data file called chick1.txt. And this is the weight of chicks, not young lady chicks, little chickens. So, and I included this in your frame so you can either work along with this or do this at your own pace. So you've got your chick1.df standing for data frame. You bring in your table like usual, and you look at the structure. So you see here you've got treatment. You've got a factor with 3 levels. So there's 3 different kind of levels of treatment that they, it's 3 different kind of feed that they gave the little chicks. And there's the response, it's the kind of weight gain, some kind of grams, I forget exactly what it is. And one thing, I'm not sure if I mentioned this or not, but in order for ANOVA to run, the treatment has to be a factor variable, but make sure you do that whether I told you that or not. That is always true. Okay, Bartlett test has been around for 100 years. So anyhow, you just put in Bartlett.test and you put in as though you were just setting up your formula. So you have response tilde treatment and the data chick1.df. And here's your output. So you have, for homogeneity of variances, that means equality of variances. It has its test statistic, and it gives a p-value, and that's what we're really interested in. So we have a generic test. So we're comparing sigma 1 equals sigma 2 equal however many there are versus not all sigma sub I are equal. So it's the same number of treatments that you have in the population. Use the p-value from the test as your test statistic. If p is less than alpha, then we reject HO, and of course you have your conclusion. So no big surprises there. In this particular problem, we're going to have 3 treatments referring to the 3 levels. So we have sigma 1 squared equal to sigma 2 squared equal to sigma 3 squared versus not all the sigma sub I are equal. And the p is equal to 0.3751. If p is less than 0.05, then we reject HO, and we fail to reject HO. And ideally, we fail to reject HO. You'll see why in a little bit. So when you have equal variances, we can go ahead and do our usual stuff. And we'll continue. The reason being, so we're going to go ahead and do our analysis of variance. We can do our intervals, even though I didn't do it in this particular case. I just did the regular analysis of variance. If you don't do that, you can do a proxy for analysis of variance, but you can no longer do the intervals or anything. Okay. So here's your analysis of variance like we always do. AOV response tilde treatment, and there's your summary. There's your p-value where it has PR greater than F. And then here is our regular test, just like always. So you're comparing means, mu1 equal to mu2 equal to mu3, referring to the 3 different treatments. versus not all mu sub I are equal. P is equal to 0.0079, ties into that. If P is less than 0.05, then we reject HO, and we do. Okay, then we would do our intervals and do all our usual good stuff. And we know, of course, that when we reject, we are saying we are saying, yeah, some are not equal to some of the other ones. We are not saying explicitly which ones are not equal to the other ones. That's what the intervals are for. Okay, good. So that is from that particular data file. Let's pull one from a data set that is actually within R. So the data set is called insect sprays. It's one word, insect sprays, where the S in the sprays is capitalized. It has two variables, count and spray. The count is the number of dead insects. I know this class would like that. We always like kind of macabre data sets. And the spray is the factor that represents the type of spray. There are 6 kinds of spray. That is, K equals 6 treatments, or you can think of this as 6 populations. We start out with the Bartlett test. So here we have our data insect sprays. Notice that's in quotes. So you have Bartlett.test. There you have your count tilde spray. Just like always, there's your output. Okay. And there's your p-value, 9.085 e to the minus 05. Uh-oh. So, 6 populations. We set up this. We have sigma 1 squared equals sigma 2 squared. It's going to go up to sigma squared, or sigma 6 squared, versus not all sigma I are equal. Our p-value is, so if we were going to write this out, it would be 0.0009085. If I'm not saying it again. If P is less than 0.05, then we reject HO. We definitely reject HO. So we can't use our regular AOV function. It's based on the assumption of equal variances. What are we going to do? Panic. Good. Aha! We don't have to panic. There's a very fine function called oneway.test. It works with the unequal variances. Essentially, it's a generalization of that Welch 2-sample test that we have we've seen already. The hypotheses are identical to those that we have in the previous section. The function we use is different. As I mentioned, we can't do the more extensive testing that is in terms of the intervals and things like that. The name of the function is oneway.test. So we have oneway.test is count tilde spray. Data is equal to the insect sprays. Okay, so you don't get the pretty table or anything. Excuse me. Oh, goodness me. There's your p-value, though, so that's what's important. Your hypotheses themselves will look the same. You still have the mu1 equal to mu2 equal to, and it's going to be 6. I should say that is mu of 6. So you're going to have the same number of mu's as you had of sigmas. That's as it should be. Not all mu sub I are equal. Then the p-value is that 7.999 e to the minus 12. No, I'm not going to say that. If P is less than 0.05, then we reject HO. We most certainly do reject HO. So not only are the variances not equal, the means are not equal. And that's as far as we can go on that. But at least we can make it that far. Until that one-way test was available, you couldn't even make it that far. So essentially, the data set that you had was meaningless. So at least you have this much. Okay? Hope this helps.